Today we're going to learn about Hess's law, which is covered in section 17.4 of your text, but not all that well. I'm going to use materials from page 9 of your homework packet, which is this document right in front of you. And then there's a quote unquote toolbox on page 10 of your homework packet. We'll use this information to do pages 5 and 6 in your homework packet. So I'm going to go to the bottom of this equation, in this last equation where it says CH4 plus O2 or 2O2 forms CO2 and 2H2O. We burn methane in this room. Essentially, our Bunsen burners are methane. We combine it with oxygen in a combustion reaction, forms CO2 and H2O. It's an exothermic process. It gives off 191.7 kcals per mole of each reactant, meaning if I had 1 mole of CH4 molecules, 2 moles of O2 molecules, it would form 1 mole of CO2 molecules, 2 moles of water molecules, and give off 191.7 kcals. Notice this number is bigger than a lot of the phase change ones because chemical changes typically have more energy than phase changes. Now, if we were trying to figure out this amount of energy, how would we do that? By an experiment, I could heat some water. If I knew the grams of water and I knew how much the temperature changed and I know the heat capacity of water, I could figure out how many kcals of energy I have, divide it by the moles of, let's say, CH4 I used, and I could figure this out. But let's say you are not allowed in the chemistry lab because you're at home for quarter 4 because nobody can go anyplace. How could you get that? By using that toolbox on page 10 of your homework packet. So what we're going to do is look at the component parts that make up this equation. And I'm going to especially focus on the compounds CH4, CO2, and 2H2O. So CH4 is the first product that I have down here, and I'm going to look for that in my toolbox on page 10. And I'm going to bring that over here, and I'm going to say these are heats of reaction, by the way, and these are component elements that combine to give up this compound. And almost any compound we have has been measured, so you could find this online or in a textbook or whatever. I just have a limited toolbox for the ones we're going to use. And I look at the only equation that has CH4 and it looks like number 3. Now, in the equation in the toolbox, CH4 is written as a product, but in my equation right here, CH4 is written as a reactant. So just like when you screw something in, you turn the ratchet one way. If you want to unscrew it, you turn the ratchet the other way and unscrew it. So the thinking is if C plus 2H2 combines to form CH4 and give off 17.9 kcals, like in number 3, you could say CH4 plus 17.9 kcals is going to give you C plus 2H2, and it does do that. So I'm going to write that backwards. I'm going to say C plus O2 forms 17.9 plus CH4 forms C plus 2H2 up here. I took 203, I reversed it. When I keep track of delta H's, endothermic processes are positive because I'm adding it to the equation. So I'm going to put a plus 17.9 up in the corner over here, which I don't know if you can see at this point. We'll get back there in a bit. Okay, the next thing is I'm going to look for CO2. Where is CO2? It looks like it's tool number 2. It's the only one with CO2 in it. C plus O2 forms CO2 plus 94 kcals. That exactly matches up to this CO2 right here. It's on the same side. So I'm just going to write it down just as I see it. C plus O2 forms CO2 plus 94. Okay. Now the next compound is 2H2O, and it's 2H2O as a gas. So I'm going to look for H2O as a gas in my toolbox. And I see number 6, I got H2O as a gas, 7H2O as a liquid. I want to pick number 6. H2O gas is a product in the toolbox, and it's a product here, so I'm going to keep it in the same direction. So H2 plus O2 forms 2H2O plus 57.8 kcals, which I get from the toolbox. However, we want to get 2 moles of H2O, so we're going to use this equation twice, or we're going to double everything in there, including the energy term. 2H2 plus O2 forms 2O2 plus 115.6 kcals. So now we're just going to check to see if we did everything right. I didn't do anything with this O2, but I'm hoping it'll cancel out and things will work out with this equation. So it's kind of like you're adding simultaneous equations. The first 3 equations here are going to add up to equal the final equation. I'm going to cross out like terms on the same side or on opposite sides of the equation. Like this C and this C cancel out. The 2H2 here cancels out with the 2H2 there. If I do that, notice what's left on the left side. It's CH4 plus O2, which is CH4 plus 2O2. Notice what's left on the right side, CO2 plus 2H2O. So I got either the mechanism for this reaction or at least a possible mechanism for the reaction. Either way, I have something that will give me the right amount of energy. So what I'm going to do then is I take these things, I see they add up to equal the final equation. Then I'm just going to add up the energy amounts that I have right here. So the first one is 17.9. That's an energy gain. The last 2 are energy losses. So it's kind of like I go to Mystic Lake, I win $17.90. All right, I go back. Then I release $94. And then I go back again and I release $115.60. Do I have a net profit or a net loss? A net loss. Overall, I take 94 and the 115.6, add those up, subtract the gain of 17.9, and I actually released $191.70, or in this case, CH4, when combined with 2O2 forming CO2 and 2H2O, released 191.7 kcals. I'm just going to slide this over a little bit so you can see the delta H's, and notice delta H is, if it's on the left-hand side, it's positive. On the right-hand side, it's negative. Instead of saying how much energy is gained or lost, I can just say delta H is negative 191.7, and that means I released 191.7 kcals in this reaction, which is what we'd expect in an exothermic reaction. As long as we're talking about that, there's this little distinction down here. Exothermic means energy is released. It feels warmer because it gives off energy to the surroundings. And if you put your hand in there, your hand is part of the surroundings. So it's giving off energy to your hand. The energy is written on the right-hand side of the equation, or delta H is considered negative. If you look at an endothermic process, you'll see all the opposite of those things. Okay, just going back to some rules that you have to do this, and they're right above your equation. We did all these steps. We determined what things will add up. Usually it's the compounds you focus on. The oxygen cancels out by itself. You only had to reverse one equation to match it up. That was the first one involving the CH4. And then the only one you had to multiply to get to 2 was the H2O equation. But then you add up simultaneous equations, cross out like terms, determine the net energy, and so on, like we talked about. So that's a reminder about steps right there that you'll have right in front of you. So I'm going to finally close with just a picture view of this. And I'll put this right here. And I'm going to talk about this as potential energy on this diagram. And think about it, the energy stored in bonds. So I got CH4 and 2 O2s. And it does take energy to rip the CH4 from those hydrocarbons. So I have to rip some energy. It's going to take energy. That's the 17.9 kcals right here. Then I have, what do I have left? I have C plus 2H2 and then plus the 2 O2s right there. So now what's going to happen is is that carbon's going to combine with the O2 and going to form CO2. And CO2 is very stable, so that's going to release a bunch of energy, a lot more than we used initially. And then the H2 is going to combine with the O2 and release a bunch more energy, and that's this amount right here. So even though initially you had to add 17.9, you release 94, you release 115.6, at the end of the day, this overall process releases 191 kcals per each 0.6 for each mole of a reaction. So if I said CH4 plus 2O2 forms CO2, 2H2O, it would release 191.6 kcals, or we could say delta H equals negative 191.6. Thank you.